Welcome to Mission Ridge, the ski area right over my shoulder, high up above Wenatchee, Washington. And our guest today is Mike Eddy, who's going to look at these rocks with us. This is part of the Leavenworth Fault Zone. There's all sorts of interesting bedrock that Mike has been studying over the last few years, and he continues to work about North Cascades geology and how the Eocene period fits into all of this. Thanks for joining us. So we're still three people and sharing two mics, but we're gonna try to scramble up this. We've got some beautiful looking class. I think it's worth it. Oh yeah. Work the legs. So just to include as many people as possible, here we are at the Mission Ridge ski area above Wenatchee, and yet we're looking at rock from the Stewart Range.
Right, so each of these blocks that looks like a piece of granite is either a tonalite or a granodiorite.
What's a tonalite, please?
Tonalite is a type of granite that doesn't have a lot of potassium feldspar in it.
Okay.
Very, very common in arc settings, subduction zone settings.
Okay.
Yeah, so these blocks are all granitoids. These tonalites are granodiorites.
Yep.
And it's long been suspected that the obvious source for them was the Mount Stewart batholith, because they honestly look exactly like the Mount Stewart batholith.
Let's not overthink this, right?
Yeah. But we,
we can move. There's stuff coming down. Whatever you're comfortable with.
Yeah, I think it's just the wind.
Okay.
But we actually had an undergraduate that worked on a project here who chipped off some of these blocks and did uranium lead dating. So that matches the Mount Stewart emplacement age.
Do you remember a number?
Do you remember, Erin? I think
she had class from both parts of the Mount Stewart, so I think they were like 92, 93
Okay.
range.
Yeah, let's get out of here.
it's amazing what the wind can do.
Yeah.
But she did uranium lead. The age matches exactly with the southern bit of the Mount Stewart batholith. She did aluminum and hornblende barometry, which tells you the pressure at which the magma that formed these rocks was in place.
Yep.
That matches the southern end of the Mount Stewart batholith directly. So we now have sort of multiple lines of evidence that these blocks came from a part of the Mount Stewart batholith that's exposed above Leavenworth, which is something like 30 kilometers along strike of this fault away today.
Here that you need.
Well, we're happy to think that this sort of thing likely continues underneath the Columbia River basalts for some distance. I don't know how we'd resolve that unless someone wants to drill to granite breccia, which I can't imagine anyone would want to do.
Well, it's one thing to enjoy an outcrop, it's another to plug it into a possible strike slip fault with 30 kilometers of offset. It's another thing to plug it into a more regional story. It's another thing to go all the way offshore and have some sort of ridge that's sending stuff going up to Alaska at the same time it's sending stuff here.
Yeah, so I think, that's definitely, I probably don't even want to drag Erin into this, but I think having the triple junction down here, having a spreading ridge intersecting Washington, and having the Kula or the resurrection plate moving very obliquely relative to North America, provides a good mechanism for sort of clipping little bits of North America off and sending them up to Alaska. But that is definitely not. There's lots of discussion about whether that
Sure.
happened. Yeah, that's not necessarily a consensus view.
So Erin, you're starting your PhD, or you're finishing your first year with Mike in Purdue, and was Alaska part of your, is it still part of your plan?
Yeah, it's still part of the plan. We just weren't able to get out there this summer.
For obvious reasons,
So,
right?
yes, unfortunately.
So earlier this week or last week or whatever, you were over the Olympics. What were you doing in the Olympics, and then were you going to try to find similar stuff up in Alaska?
Yeah, that's the idea. There's this idea that there was a oceanic island plateau that had collided with the coast of Washington just prior to the formation of the Trumpstick Basin, and that there's also this hypothesis that part of Alaska, the Yakutat terrain, was once part of that plateau, and that it's since then been translated up north and is now currently colliding with southeastern Alaska. And so part of my PhD, or my PhD focus, will be to look at the sedimentary rocks that are sitting on top of Silesia, which is the interpreted oceanic plateau sitting off of Washington and through Oregon, look at those sedimentary rocks there, and then also look at the sedimentary sequence sitting on top of Yakutat and see if we can recognize where the sediments were coming from, what the basins looked like. Was there a point where the depositional environments were similar? We could see sediment routing systems that would suggest that they were once part of the same plateau, and then could we see when the Yakutat terrain broke off and started its northward journey to its current position in Alaska.
So there's a potential for an identical twin up in Alaska of the Silesia and some of those sediments that you had here in the Olympics?
Yes.
So that's that idea has been around for a while, but Ray Wells at the USGS really in 2014 sort of tied everything together nicely. Yes. And that sort of spurred a lot of our questions about, well, can we now go in and really test that if we can go up to Alaska and sort of better characterize some of the sedimentary units in the Olympics.
I'm having a hard time picturing where the sedimentary material is coming from, if it's just this big ocean plateau sitting out there in the water. So is it after it docks that the sediment's coming off of North America?
So that's a big question, where the sediment's coming from, and whether or not it was just being locally sourced from the oceanic plateau, or whether or not it's coming from the continent. That's part of the project, is to figure out where these sediments were coming from and tie it all in with previous work that's been done there with paleocurrent and compositional data, and then we can kind of bracket it using high precision geochronology, dating some of the volcanic material in there, and try to see that transition of where sediments were originally being derived from and then how it has changed.
Super cool.
But one of the interesting things that we noticed as we were reading theses and looking at maps while we were out in the Olympics is that there are some sizable units that appear to be derived from the west out in the Olympic Peninsula, and there's nothing to the west now. So Erin has her work cut out for her, but there's some interesting features up there that are ripe to be explored.
Am I getting what you're saying? Sediment that's younger than Silesia accretion that had a source to the west of Silesia that's not there anymore.
So, but post-date the accretion, and then then it's not there anymore.
Yeah, so there's some interesting units out there that seem like they're derived from the west, and there's nothing there now.
So you go north to look for it? It has to be north, right? Like, where else would you look?
That's where we look, yeah.
I'm in.
Yeah, sure. So I was working on the same project as a PhD student that Erin was working on as a master's student. So this idea of a big period of transition in the Eocene, which we thought might be related to triple junction being offshore here, just to the west here along the coast of Washington. So what I mean by triple junction is I mean a place where there is an oceanic spreading center that intersects a subduction zone in this case. So we'd have the Farallon plate, or the, I guess which we now call the Juan de Fuca plate, the little remnant of it. A plate to the north of that, which was either the Kula or the Resurrection plate, both of which are totally gone now. They've been subducted, they've gone down the hatch. And then North America. And so when this tectonic situation occurs, you basically change all the boundary stresses on the upper plate. So in this case, North America. You can have big changes in the style of volcanism, the style of magmatism. It's as a triple junction passes, it's a big period of transition. And so for the last 10 years, we've been really interested in the late Paleocene, the Eocene, going into the Oligocene, thinking about this period of transition where we think we know something about the Cretaceous arc and how that operated. We definitely know how the modern Cascade arc is operating, but there's this window of a few 10, 15 million years between them where there's a lot of weird stuff happening. And we're trying to piece that together.
Even this far east, I mean, we're in Wenatchee, and there's ramifications from what was happening offshore, essentially.
Right, yeah, so...
Let's take a walk a little bit, would you mind?
Yeah. So I think the Chumstick Formation is probably one of the biggest manifestations of a change of stress on the plate boundary in the Eocene. Yeah. So previously we probably had subduction of the Farallon plate that may have been a little oblique and driving some strike slip faulting. But as the triple junction passed here in Washington, we're very likely juxtaposed with either the Kula or the Resurrection plate, which when we do plate reconstructions, we know was moving highly obliquely relative to North America. And so once you juxtapose those two things, those two plates, you have a strong push for dextral or right lateral strike slip faulting. And so basically right as we see all these changes happening further to the west that we attribute to the passage of this triple junction, you start opening up the Chumstick Basin and depositing the Chumstick Formation. And the way that we've interpreted, which is a little bit of a modification from previous interpretations for this basin, but not too much of a modification, is that this is one big pull-apart basin between the Intiat and the Leavenworth faults, which were both acting as big right lateral strike slip faults.
As this submarine ridge is diving beneath us, and there's kind of an extensional regime and the kind of the strike slip thing happening at the same time. That's all. Those ideas go together?
Yeah, so you can think about it as when the Farallon plate was the subducting plate just to the west of here. You didn't have a huge drive for strike slip motion, maybe a little bit, but as soon as that became the Kula or the Resurrection plate, you have this big driver. It's moving really obliquely, sort of to the north along the North American margin. So as soon as that gets juxtaposed with Washington, you have this big push to have these dextral strike slip faults.
Got it. Is the lab that you had at Northern Arizona similar to what you're now dealing with when Mike's lab is built?
We actually, well, I collected the tufts and then gave them to Mike.
Oh,
And
okay.
he took them to MIT.
Okay.
And he was the one that did the age dating
Got it.
on that project. So we were able to tell a really cool story combining those ages and using the tufts as marker beds, and then combining with the facies mapping to figure out where these sediments were coming from and how old they were, how they change. And so the pattern was really distinctive of a strike slip basin. You get this northward shingling of basin sediments, younging towards the north. And that's what we're kind of talking about with these steep alluvial fans that would have then been bordering the Leavenworth fault zone. When you have movement along that fault, the basin epicenter will shift to the north as that strand becomes active. And we can see that by using these tufts and where they strike into an inner finger with these really coarse grain deposits that are along the fault. And that's also a really key thing with strike slip basins. You get these really rapid lateral facies changes from these coarse grain units to, if we walked over there, you can start to find sands and muds, and they're very different than these big boulder conglomerates.
I promise this will be it, but let's walk right over here. I'm having a good time. I don't know about you guys.
Definitely.
All right. I mean, come on. If I'm leading a trip here, I'm like, well, this is like an inclusion into something else.
It's a fascinating outcrop.
It is.
Just to have this entire unit really only had one source.
Yes.
That granite. You got the sand that's made from the granite. You got the big clasts that go from cobble to boulder, all from the same unit. So you were really just shedding off of cliffs of now Stewart. So a good analog, like we were talking about back at the cars, might be say up Icicle Creek out of Leavenworth today. You have the same rock unit that was making this, dumping all sorts of boulders and cobbles into down those big steep mountains and cliffs into the Icicle Creek area.
Wow.
So for that proposal, we're going to look at magmatic flare-ups and arcs. And so occasionally in subduction zones, the amount of volcanism, or the volume of magmatism, rises to a high level above baseline. So you have quite a bit of heat getting transferred through the crust. And so our idea was, could we make a really high resolution curve for magma addition to the arc through one of these, and then look and see how structures in the arc responded. So how did faults respond to having the crust really thermally primed and full of magma? So that's, most of that work is going to be dating a bunch of plutons in the North Cascades through two of these flare-up events, one that happened in the latest Cretaceous and then one that happened in the Eocene, which would overlap with when this sort of basin was forming.
So you've got your eye on a dozen plutons that you want to get your hands on, and or do you have samples already from previous work and you're just going to run it through your new lab, or both?
It's a combination of both, yeah. So we really have only just now started laying out maps and thinking about which plutons are well mapped, which ones are in the age range of interest. You know, where do we have gaps in data? What should be revisited? What is already well characterized?
Well, the flare-up thing in general is just a cool idea. I mean, like, you're down in Nevada and there's this big sweep of stuff coming through the state, you know? It's like, what is up?
Well, hopefully we'll get some more insights.
And so, how do you visualize me helping you? My thought is helping by kind of doing this all through the project. Like, I think something like this at the beginning is worth documenting as well as just waiting. I don't want to wait 4 years and just kind of saying, here's the results, right?
No, I think having you join us in the field would be perfect.
Okay, good.
I think one of the big problems we have is communicating what we do to the public.
Mm-hmm.
Because I go out here and map, and then I go into a chemistry lab and mess around with a bunch of solutions.
Right.
And I don't put a lot of time or thought into how best to communicate to the public.
Mm-hmm.
But
you can't do it all. I mean,
right,
you probably could, Mike, but I mean, there's not enough hours in the day.
Right. So I think, working with someone like you who already has an audience, and you've devoted a lot of time to thinking about how best to approach communication, I think this is the way that we can sort of let people know what's going on and how their tax dollars through the NSF are being spent.
There you go.
Why it's important.
There you go. So the tentative plan is a summer field season for the next 3-4 years?
Yeah. I need to recruit a graduate student to work in this, and over the next 3 or 4 years, we'll be out here every summer. And
probably just you and a student, or do you think there'll be a team of other professors and researchers that you might be in the field with at the same time?
Definitely a team. So there's Bob Miller from San Jose State.
Oh, he's been at it a long time.
I think he knows every single outcrop in the North Cascades. And Stacia Gordon, University of Nevada, Reno.
Mm-hmm. Good.
And she already has a PhD student that's working on this project, whose name is Lizzie, and I don't know her last name.
Okay.
Did you catch it? Yeah. Huh. But so there will be a big team.
That's a dream team, I'd say.
Well, we can aspire.
Well, we got day hikers heading up to Lake something or other. They've got the ski area closed down, I guess just because of construction, but maybe because of the virus, or both. What is that lake? Lake Clara, okay. Good to know. Well, that's probably enough for today. Thanks for joining us. Hope you enjoyed visiting with Mike and learning about some of this bedrock in central Washington, which is unknown to many of us. And there's new stories in the works. We'll see you next time. I love you and goodbye.